In this video, we're going to take a look at section 5.1 on systems of linear equations of two variables. A system of equations is a set of two or more equations, all of which must be satisfied at the same time. Therefore, a solution to a system of equations of two variables is any x, y that is a solution to each equation in the system. So this is specific to just systems of equations with two variables, but that can be generalized. And so the generic concept of a solution to a system of equations is anything that is a solution to each equation in the system. If there's three variables, you'd have to have three values, x, y, and z. But for two variables, you just need two values, x and y. All right, let's take a look at some examples. So determine whether the point 4, 6 is a solution set to the following system of equations. So for this to be a solution to the system as a whole, it has to be a solution to each equation in the system. So there's kind of two levels here. It's kind of a meta thing where there's being a solution to the individual equation versus being a solution to the system of equations as a whole. All right. So for the ordered pair 4, 6, the first value is 4, so that's our x value. The second value is 6, so that is our y value. So they're telling me here that x is equal to 4 and y is equal to 6. I want to check to see if that is a solution to the system of equations. And for it to be a solution to the system as a whole, we have to make sure it's a solution to each equation in the system. Now, to build up a little bit of suspense, I'm going to start with the bottom equation first. I normally wouldn't do that, but you'll see why I'm doing that in just a minute. So let's check that bottom equation first. We have x minus y equals -2. Let's check to see if these two numbers are a solution to this equation. And so we will have x equals 4, so I'll plug in 4 for x. I'll have y equals 6, so I plug in 6 for y. I get 4 minus 6 here, which is -2, and so I get something true. I get -2 equals -2. That's true. So 4, 6 is a solution to this equation, but that doesn't make it a solution to the system necessarily. It has to also work in the other equation. So let's check those numbers in the other equation. We have x plus y is equal to 12. We're going to plug in 4 for x. We're going to plug in 6 for y. We get 4 plus 6 here, which is 10. 10 does not equal 12. So I'm putting an x here as in that's bad, right? This is not true. And so 4, 6 is not a solution to the top equation. And so even though it works in the bottom equation, it is not a solution to the system as a whole because it doesn't work in every equation in the system. And so our answer here is no, 4, 6 is not a solution to the system of equations, even though it was a solution to one of the equations in the system. All right, so again, it has to work in both. That's the point I'm trying to make there. All right, let's check the bottom one. So why don't you try this one first? So pause the video. Check to see if 3, 4 is a solution to this system of equations. We have -2x plus y equals -2, and we have 2x plus y is equal to 10. And then resume the video to see if you came up with the correct response. All right, so let's check the first equation here. So we have x is equal to 3, y is equal to 4. So we'll check the top equation. I guess I'll just go ahead and write it out. We have -2x plus y equals -2. We're going to plug these numbers in. So we'll have -2 times 3 for x plus 4 for y. That's going to give me -6 plus 4, which gives me -2 equals -2. And so the ordered pair 3, 4 works in the first equation, but that isn't necessarily sufficient for it to be a solution to the system. We have to also check the second equation. So let's go ahead and check that one. We have 2x plus y is equal to 10. We'll plug in 3 for x, and we'll plug in 4 for y here as well. And let's see what we get. We get 2 times 3, which is 6. 6 plus 4 is equal to 10. And so we get 10 equals 10. We got negative 2 equals negative 2. It doesn't matter what these numbers are. 10 isn't really meaningful here. What's meaningful is we get a true statement. 10 is equal to 10. That's the meaningful part. Negative 2 equals negative 2. That's the meaningful part. This is true. This one's true. And so 3, 4 is a solution to both equations, which means that yes, 3, 4 is a solution to the system, since it's a solution to each equation in that system. So let me go ahead and write that out, and then we are done. So I'm sorry my handwriting got a little sloppy there. All right. So that is how you would do those problems. All right. Now, what's happening with these problems is they are giving us an ordered pair to check, and then we can plug it in to see if it works or not. That is not the ideal method for finding a solution to a system of equations. You don't want to just make a guess and plug the numbers in to see if you're right or wrong. So we're going to develop some methods for helping us find the solutions to the system of equations. And in fact, there are 3 methods that we can use. So you can use graphing to find a solution to a system of equations when there's just 2 variables. In theory, you can do it when there's more than 2 variables, but if you have more than 2 variables, you're working in more dimensions. Excuse me, I need a drink real quick. So for example, 3 variables, you'd have a 3-dimensional graph, and finding the solution in a 3-dimensional graph. First of all, it's hard to graph in 3 dimensions, but then having to graph multiple equations in 3 dimensions is just not a very feasible or practical way of doing it. So, but for 2 variables, graphing can work. So we'll talk about how to do that. Then we have this method called the substitution method, and we have this method called the elimination method. So we will talk about how each of those work in the next 3 examples. All right. So let's talk about graphing first. The way the graphing method works is you take each equation and you have to graph it on the same Cartesian coordinate system. So let's start with the first equation. We have x plus y is equal to 8. We need to graph this equation. These are linear equations, which means when we graph them, they should graph as straight lines. To graph a line, you just need to have 2 points. So it's a review, right? We talked about graphing lines way back in chapter 1, really as a review in chapter 1 also, because that's something you should have known already before taking this class, right? So it's a review of a review, but this is, something we've done a few times. We also did a little bit of graphing lines in chapter 2. And so just like any other topic in this course, you can't forget anything. You can't just learn it for the moment and then forget it, because they will often use concepts later in the course. Right, so to graph a line, we need 2 points. The quickest 2 points we can get from this type of equation would be the x and y intercepts. Right, so to find the x-intercept, we plug in 0 for y, and then we solve for x, and we just get x is equal to 8, right? Because the 0 just goes away, and immediately you get x is equal to 8. And so we get the point 8, 0. We could also do the y-intercept, right? By plugging in 0 for x. That 0 just goes away, we get y equals 8. So that's why I like to do x and y intercepts when the equation is in this form, because one term just disappears and it's pretty easy to solve for the other variable at that point. Right, and so this is going to be the point 0, 8. All right, so we're going to plot these 2 points. I'll do these in red since that's the color that most of this is in, so we can keep track of which line is which. And so this is going to be for our first equation. We have this one's 0, 8, and this one's 8, 0. And then we will connect those 2 points with a straight line, which I was going to try to do manually, but I'm afraid I would probably botch it. So I'm just going to use the straight line drawing tool that comes with the software. And it's still kind of off the mark, but I think we'll make this work. Okay, so there is the line for this equation here. That's one equation and one graph, but we also have to graph the other equation, right? Whoops, I guess I need to stop using the straight line tool. Let's go back to just free form. Okay, So we have to also graph this equation here. So I would like you guys to try this one. So do the same thing. I mean, you don't have to. You could also do the slope and the y-intercept if you wanted to graph it that way, but you'd have to do some work to get there. But however you want to try to graph it, graph this equation on the same Cartesian coordinate system. So pause the video, see if you can figure out what the graph looks like, and then resume it to see if you came up with the right graph. Now I'm going to use the same method I did down here, but I'm not going to write out the same amount of detail because, again, what I like about this method is you can figure it out kind of just by looking at the equation, right? The x-intercept, you plug in 0 for y, so that term goes away. You get x is equal to 6. So you should get 6 comma 0 if you did the problem this way. For the y-intercept, this one's a little bit more difficult than down here. You're going to plug in 0 for x. So x is going to go away. You'll get negative y is equal to 6. So to solve that for y, you divide the negative sign to the other side. So this time you actually have to do some work to solve it. It's a little bit of work, but it's still a little bit of work. And you divide by negative 1 on both sides, you get y is equal to negative 6. Right? And so you're going to get 0 comma negative 6 for the y-intercept. And so that's the 2 points we're coming up with for the intercepts, if that's the method you use to graph this line. So I'm going to plot these 2 points. 6 comma 0 would be right here, and then 0 comma negative 6 would be down here. So even if you use a different technique, you might come up with different points that you actually got, but it should still create the same line. It should be right here where you're seeing this line show up. So if your line is going in some other direction or is located somewhere else, you did it incorrectly. All right, it should look like this. All right, even if your points are a little bit different. Okay, so let's connect these 2 points with a straight line. Hopefully I'll do a decent job there. I think good enough. All right. Now, how can we use this graph to help us find the solution to the system of equations? So remember what we're looking for here. We're looking for an ordered pair that is a solution to each equation in our system. We want it to be a solution to the top equation, and we want it to be a solution to the bottom equation. Now think about what these graphs are representing. The red line, every point on the red line is a solution to the bottom equation. Sorry, not the bottom equation, the top equation. X plus y is equal to 8. So every point on this red line is a solution to this equation. Every point on the green line is a solution to the bottom equation, to this equation. We are looking for an ordered pair that is a solution to both equations at the same time. And so you will find such an ordered pair where the two graphs cross each other. Right? So here where they intersect is a point that is on the red line, so it's a solution to the top equation, and also on the green line, so it's a solution to the bottom equation. And so it's what we're looking for, something that is a solution to both equations at the same time. And this point is located at 7 for the x and 1 for the y. So 7 comma 1 is a solution to both equations at the same time, so it is a solution to the system of equations. So that's the answer that we're looking for. So the synopsis here is the way you find the solution to a system of equations by graphing is by graphing all of your equations on the same Cartesian coordinate system and finding where they intersect each other. All right. Okay, so that's the graphing method. We also have what we call the substitution method. So the way this method works is when you're given two equations like this on your paper, we can see both equations simultaneously, right? So when I look at this screen, when I read the paper with my problem on it, I can see there's two equations here, and I want both of them to be true at the same time. So we're aware of that. But if you think of it from the equations perspective, these equations, they're in different universes, right? They don't know about one another. So we want 9x plus 6y to equal 0, right? This equation knows that. It knows 9x plus 6y is supposed to equal 0. That's all it knows. It is unaware that we also have another equation just below it with a different set of requirements, right? So the bottom equation is telling us we want x to equal 26 minus 5y. So we are aware of both of these conditions that we're trying to satisfy, but the top equation is unaware of the bottom equation's condition, right? It doesn't know what the bottom equation wants. So we want to make it aware. I want to take the top equation and make it aware of the bottom equation, right? And the way you do that is by substitution, right? The bottom equation is telling me that we want x to be the same thing, equal to, right, the same thing as 26 minus 5y. I'm going to let the top equation know about that, right? So here's my top equation. I'm going to let the top equation know that this x is supposed to be the same thing as 26 minus 5y. It didn't know that before. But by taking its x away and putting 26 minus 5y in its place, now the top equation is going to be aware of that second condition that we have. So everything else about this equation is going to stay the same. I'm going to keep the colors the same. In fact, just to make it clear, I'm just going to copy the rest of this down. Right? I have a 9 here I'm going to copy down. That's being multiplied to this, plus 6y equals 0. Right? The rest of it copies down. But in place of the x, we now have 26 minus 5y. So now we have both conditions present at the same time. Right? Here's where x was located. We have x being the same as 26 minus 5y, right? That's the bottom equation. We also have 9x plus 6y equals 0, right? So we have both conditions together at once. So when I go to solve this equation, any information I get out of it has to pertain to both equations being true at the same time, since we have both equations present at the same time in constructing this, right? And so I'm going to solve this equation, and I can do that now because now I'm down to just one variable. I can solve for that variable. I'm going to solve it for y. So we're going to distribute the 9 into the parentheses. I'm going to get a big number here. Let's see. Can I figure this out without a calculator? So it's going to be 180 plus 54. It's going to be 234 is what I'm coming up with, but I don't trust myself. So I'm going to go ahead and use a calculator. All right. So let's go ahead and do this calculation real quick. So we're going to have 9 times 26, 234. I got to learn to trust myself a little bit better. All right. Minus 45y, right? That's an easy one. 9 times 5 is 45. And then this copies down, plus 6y equals 0. I'm going to go ahead and do two things at once. Usually by this point, students are pretty comfortable with, this type of equation that you can kind of do multiple things at the same time. I'm trying to get y by itself, so I'm going to combine these together. But while I'm at it, I'm just going to go ahead and subtract the 234 to the right-hand side, right? Because that's the next thing I would want to do anyways. So since it doesn't have a y, it doesn't belong over here, move it to the right-hand side of the equation. So we're going to get negative 39y, when I combine these together, equals 0 minus 234 is negative 234. And these numbers are looking kind of bad. Unfortunately, it's possible that you can have a system of equations where your answers don't work out very nice. There's no reason why these have to be nice, easy numbers. However, when most of the time it does work out nice, so usually you'll get a whole number. Or if you do get a fraction, they're usually of a nicer variety, right? So like 1/2, 9/5, maybe something complicated like that, but nothing. If you get a fraction like 137 over 19, that's probably a bad sign that you did something wrong, right? So if you're going to get a fraction, usually they're more reasonable fractions. So I kind of feel like if this doesn't reduce, I'm going to be a little bit suspicious about it if it stays looking like this. But if it reduces to something nice, or if it ends up just being a nice answer, then we should be good to go. So again, I'm not really sure what this answer is. So we'll take 234, divide it by 39. We get 6. So it works out really nice, even though it looks kind of scary. Now notice I didn't bother with the negative signs because I know negative divided by negative is going to be positive. So this will be positive 6. So we get y is equal to 6. That is not the final answer to this problem. When you're giving a solution to a system of equations, you have to provide a value for x and a value for y. So solutions here have to have two values. We just found one of them, right? We got y is equal to 6. Oh gosh, I can't believe I just did that. Sorry, I moved the border of where I was recording. Let's see, can I move it back? Oh, I'm going to pause it and see if I can move it back to where it was. Sorry. Okay, so I think this is about where the screen was to begin with. So sorry about that if that was jarring to you. Okay. And so we got y equals 6, but we still need to find x. Right? So how do we find x? Well, once you find the value for y, you can get x by taking your value for y and plugging it back into one of the original equations. It really doesn't matter which one you use. You'll get the same answer either way. So let me put it this way. It doesn't matter in terms of the answer you're going to get which one you use. So whether I use the top equation or the bottom equation, I'm going to get the same answer for x either way, if you have the right answer for y. So that would be a good way to double check is if you plug in 6 for y here and 6 for y here, and you get two different answers for x, this is not the right value for y. You should get the same answer from either equation. Where it does matter is the amount of work you're going to have to put in, right? So if I use the top equation and I plug in 6 equals y here, well, then I'm going to have to subtract that to the other side, divide by 9. It's going to be some work. The bottom equations already solve for x, which is what I'm looking for. All I have to do is dump 6 in for y and just simplify the right-hand side, and I immediately get my answer. It's already solved. So I'm going to use the easier of the two equations to get my second value. That's what you want to do. So we get x equals 26 minus 5 times y, which is 6. We just found out. So we're going to get 26 minus 30, which is going to be negative 4. So x is equal to negative 4, and so that's going to be my value for x. Now when I go to type this into Math Excel, it wants the answer as an ordered pair. You have a value for x, a value for y, so you can write that as an ordered pair. The x value goes first, so be careful about that. I found the number 6 first, and then I got negative 4, but my answer is not 6 comma negative 4. I will get students that make that mistake, right? Because that's not the order we put these numbers in. It's x value first, y value second. So x is equal to negative 4, that one goes first. Y is equal to 6, that number goes second. And that's what you would type into Math Excel. All right, so that's how the substitution method works. Essentially, you take one equation and plug it in to the other equation. Excuse me. All right. The last method we're going to talk about here is called the addition method. I might have called it something different on this previous screen. Yeah, I called it elimination method. Elimination is probably the more common name for this method, but this textbook calls it the addition method. It's the same thing. So what we're going to do for this system of equations, we have x plus y is equal to 2. We have x minus y is equal to 16. Is we are going to add the two equations together. That's why it's called the addition method. We're going to add these two equations together. And the way you add equations together is you add the left-hand sides and you add the right-hand sides. And the rule for that, the conclusion from that, is that the result you get from the left-hand sides being added together and the right-hand sides being added together is that they would still have to be equal to each other. So when you sum up the left-hand sides and you sum up the right-hand sides, the results are still equal. Right, so I'm going to add the left-hand sides here. I'll combine like terms. So we get x plus x, which will be 2x. And then when I go to combine the y's together, we get y minus y. They cancel each other out. This is why it's also called the elimination method, because this is what needs to happen for this method to be effective. You have to get a variable to eliminate. You have to make a variable cancel out. This problem was set up for that to automatically happen for us. So this is actually a really easy version of this type of problem, right? The y's are already set up to cancel each other out when you add them together, right? So the y's cancel each other out and they're just out of the picture. I add the right-hand side of this equation together, these equations together, 2 plus 16 is going to give me 18. And what I know about this operation is that the results would still have to be equal to each other. So these are still equal. So 2x is equal to 18. And now, since y is out of the picture, I can solve this for x. I'll divide 2 on both sides, and I get x is equal to 9. Now you might say, wow, that was so easy. Why didn't we do the previous problem that way? Well, it wasn't really set up to be done that way, right? So trying to do the elimination method on this problem is going to be more challenging. You have to get your x's and y's to line up, which these are not. You'd have to add the 5y over here. And even if you did line up the x's and the y's, they are not prepared to cancel each other out. You'd have to do some work to make sure one of the variables got canceled out. So you could do elimination method here, but it would not work as well. the substitution method was the better way to do this problem. So we did this one in the easiest way that it could be done. Here, doing substitution method would be a lot more work, right? You'd have to solve one of these for x or for y and then plug it into the other equation. And, this one wouldn't be so bad that way either, but it would still be more work than what we had to do. Other problems, substitution method would be a horrible way to do it, but elimination method works better, which is why we're learning both methods. So that's the point I wanted to make, is why do we have to learn multiple ways to do the same problem? Because one method works better on some problems, the other method works better on other problems, and it's good to know both methods and kind of learn when to apply which one. All right, so x is equal to 9. We're not done yet. We still have to find y, right? Remember, you have to have two values in order to have a solution to a system of equations. So we have to plug this back into one of our original equations. This one's kind of a toss-up as to which one is the better one to use. It, in theory, doesn't matter which one you use. You should get the same answer for y either way. But I'm kind of shying away from the bottom one because it has that negative y. So I'd have to deal with that negative sign. I kind of don't want to. So I'm going to plug this into the top equation instead. But it's my choice. I could plug it into either one. I'm choosing the one that I think will be easier to work with. All right, so we have x plus y is equal to 2. Whoops, I'm putting 9. I'm skipping ahead of myself here. And then I'm going to plug 9 in for y. All right, so that's where I want to put the 9. And then I can solve this I'm saying the wrong things, I think. I'm plugging in 9 for x. I don't know if I just said y a moment ago. I'm sorry if I did. So I'm plugging in 9 for x, and then I want to solve for y. I think my mind's like one step ahead of where I'm actually at on the screen. All right, and to solve this for y, we will subtract 9 from both sides. So pretty easy. All right, we get y is equal to -7. And so we take these two numbers, put them as an ordered pair. X always goes first, y goes second. And this is what my final answer is, as an ordered pair. All right, so we have a couple more things to talk about here, concept-wise. And we do have some word problems at the end. That's very common with system of equations. There's a certain class of word problems that work well with system of equations. And then we'll be done. And there's a couple more practice problems in here for practicing elimination and substitution method. So far, all the problems we've done have resolved themselves, right? We solve the system of equations and we get an answer. That type of conclusion to the problem is called an independent system. All right. So an independent system is one in which there are a fixed number of solutions. So if you solve a system of equations and you get one solution, that's a fixed number of solutions. That's an independent system. So every example we have done so far in this video has been an independent system because we solved it and we got one solution every time. But that doesn't always happen. Sometimes when you go to solve a system of equations, you might end up with no solutions. In that case, we call that an inconsistent system. We have not seen an example of this yet, but we will here in just a minute. The last type that we can have, and really kind of a ridiculous type to have in this section, are the dependent systems. And a dependent system is one in which there are, an infinite number of solutions. All right, so that's called a dependent system. Now, the only way to create an infinite number of solutions when there's two variables is to have the same equation twice. And so it's kind of silly in section 5.1, the dependent system, because really all they're going to do is give you the same equation twice. They'll try to hide that by mixing it up, right? So they'll look different from each other, but when you start to dig down, you realize, well, these actually are just the same equation twice. When I graph it, I get the same line. When I solve both of them for y, they come out exactly the same. So to me, that's not really a system of equations. If it's the same equation twice, it kind of bugs me. But it's the only way to generate an example of this type. So we have to deal with it. The dependent systems become much more interesting in 5.2 when there's three variables. So we'll get to those in the next video. All right, so let's take a look at some examples of inconsistent and dependent so you'll know how to recognize when you have one of those systems. So this is a really nice problem. It looks kind of scary, has a lot of stuff going on. There's one of these in your homework because all these problems come from your homework. And it looks scary because like you have these equations, you got this graph, you got a lot of words going on here. But what's nice is they've done all the work for you. They've taken these two equations and they've graphed them for you. So the top equation is, maybe I should also follow their color coordination here, is in blue, right? So I'm going to circle this in blue. This is the top equation. It's the blue graph. And it's dashed, which I think is, you might say, why are they doing both of those things to distinguish them? I think it's for people that might be colorblind. You might not be able to tell the difference between blue and red, but then you can see the difference as solid and dashed instead, right? But it's this line right here, right? 8x minus 3y equals 0. So this line, every point on this line is a solution to this equation. The bottom equation is the red line, which is also the solid line, and it's y equals 8/3 x plus 8. So every point on the red line is a solution to this equation, right? That's how graphs work. We are looking, as a system of equations, we are looking for a point that is a solution to both equations at the same time, which means it's a point that has to be on both lines simultaneously. And you'll notice the issue with that here is that these lines are parallel, right? So these are parallel lines. They never cross each other. So they never intersect, which means they don't share any points in common, which means they don't share any solutions in common, which means that there are no ordered pairs that would be a solution to both equations at the same time. And so there's no solution. And so what does that mean? This means it is an inconsistent system of equations, which I believe it's going to ask you about after you answer this part. So it's not on my screen capture because I didn't answer the question yet. But once you answer that, then it's going to say, what type of system do you have? Because there's no solution, this is an inconsistent system. Right? So to, summarize what we just talked about, parallel lines have no solution as a system of equations. So let me maybe word it a little bit better. If your system of equation is parallel lines, there's no solution to that system of equations. Therefore, it's an inconsistent system. Right? Okay, so that's what an inconsistent system looks like graphing wise. So visually, it'll be parallel lines. All right. Let's take a look at this system of equations. Here we're being asked not to solve it, by graphing, but to solve it by substitution method. But in order to do that, and so this is kind of this problem is going to be one of our special cases. It's going to be either inconsistent or dependent, but it's also serving the purpose of, I wouldn't even say worst case scenario, but just some more obstacles for doing the substitution method. I don't know if I'm describing that the right way. The point I'm trying to make is we cannot just jump right into substituting here, because for substitution method to work, one of your equations has to be solved for one of your variables. And that is not the case here. So when we did substitution method earlier, this went too far, it was set up for us to jump right into substitution, right? The bottom equation is already solved for x. That was necessary for us to do substitution right away. Excuse me, I don't know why I feel like I don't know if I'm drinking a lot of sweet tea. I kind of feel like, Rick from Rick and Morty. It's just like, I'm not burping, but I keep it's, having some indigestion or something while I'm talking. And I'm sorry, I don't know how that's looking to you guys, but it's bothering me. So I'm sorry about that. But, and I, whenever I eat and I have sweet tea, I don't know, it kind of gives me a little bit of indigestion, I guess. So, anyway, sorry about that. So here it was set up to do substitution right away. This one is not. We have to do a little bit of work to get it set up so that we can proceed with the substitution, and it's not a lot of work here. So we have to solve one of these equations for one of the variables. I don't like to be too prescriptive there because it's really flexible. You can solve either equation for either variable. It's your choice. So again, choose the easiest thing to do. And to me, what looks like the easiest route to go is to solve the top equation for y. It's a one-step deal, right? So here's the top equation. Let's solve it for y by adding the 2x to the other side. That's all we got to do. So we get y is equal to 7 plus 2x, or 2x plus 7. You can write that either way. So that's the top equation. Now, the thing you want to be careful about is keeping track of where you just got that information, because a mistake I will see students make is they'll take that equation, plug it right back into the equation they just got it from. And in that case, you're very likely to draw the wrong conclusion. In this case, you actually would still be okay. You get the right answer either way. But you shouldn't be doing that. That is wrong. You don't want to plug this back into the same equation you just got it from. Make sure once you've solved it for y, that you substitute that into the other equation that you have not used yet, which would be the bottom equation for us here. So we're going to have the bottom equation will stay the same. We'll have 2 times, let me just write it out again here. All right, this is my bottom equation. It's the one I haven't used yet. I'm going to take this equation and plug that in for y right here. So the rest of this is going to stay the same. We'll still have 2 times x plus 1 equals, in place of y, we're going to have 7 plus 2x. Sorry, I should have did that in a different color. That was my intention to begin with. So let's do that in red, I guess. Okay. So in place of the y, we're going to have 7 plus 2x. That's the substitution. And then we'll have the minus 5 after that. Now, a lot of times when you do substitution, you'll want to use parentheses, but since nothing is going on around this y, parentheses aren't necessary. If we were distributing, if we're raising it to a power, then you'd need to use parentheses for sure. So now I want to solve this equation for x, since it's the only variable I have remaining. And so I'll start by distributing the 2, which maybe you would have already done already. I like to wait until I get to this point in the problem. So we get 2x plus 2 equals, and then here I'll go ahead and combine like terms. We have 7 minus 5, which also gives me 2, plus 2x. And if I had written it around the other way, it'd be even more obvious. But what you should realize here is that these are the same, right? You're really getting the same thing on both sides. So what's going to happen? When I go to solve it for x, I subtract 2x to the other side. The x's just cancel each other out. They're just gone. I get 2 equals 2. That's good enough. You could just stop there and draw your conclusion. But sometimes students just go all the way with this, which is, okay, now I subtract 2 from both sides, and you end up with 0 equals 0. So if you ever end up with 0 equals 0, if you just go all the way and, get all the x's to one side, all your numbers to the other side, and you end up with 0 equals 0, that's the case where you have an infinite number of solutions. All right, so this is true, which tells me I have an infinite number of solutions. Now you got to be careful about that, because when there's only one variable, infinite solutions really usually means any number works. When there's 2 variables, it doesn't mean that. You can't say, okay, infinite solutions means anything works. For example, 0, 0 is still not a solution to the system of equations. There are an infinite number of solutions, but 0, 0 is not one of them. Right? Try it out here. Plug in 0 for y and 0 for x. It's not true, right? You get 0 equals 7. This is not a solution to that equation, so it can't be a solution to the system. Right? So you can't just say, oh, it's all real numbers or anything works. Right? So what we're going to say, obviously, C is not the correct response. It's not that there's no solution. There is an infinite number of solutions. Right? A you would use if there was just one solution. Right? So the solution set is blank. We don't have just one solution. We have infinitely many solutions. So we're going to use option B. And so the way this is worded is, the solution set is any x comma y, any ordered pair, such that, so the vertical bar is read, it's interpreted, translated to such that y is equal to, and then you type in your equation here. In this case, our equation when it's solved for y is 7 plus 2x. So that's what would go in that box there. So it's any ordered pair that satisfies that equation, of which there are an infinite number, even though 0, 0 is not one of them. So for example, 1, 9 would work, right? If I plug in 1 for x, I get 2 times 1, which is 2 here. 2 plus 7 is 9, right? And so 1, 9 would be one solution to this equation, which would be one solution to the system. You could also have 2, 11, right? If I plug in 2 here, I get 2 times 2, which is 4. 4 plus 7 would be 11, right? That's also a solution to the system of equations because it works in this equation. And the thing, like I mentioned earlier, for this to have infinitely many solutions, what that really means is that these equations are the same. They look different. They scrambled it up. They used parentheses here to make it look like they were different from each other. But if you solve both of these for y, they're both equal to this. It's the same equation. So whatever works in one automatically works in the other. But you still have to find something that works, right? So these would be some examples, and that list keeps going. There are an infinite number of solutions. We could have 0, 7, keeps going in that direction as well. So there's an infinite number of solutions, but that doesn't mean any ordered pair is a solution. Just wanted to make that distinction. All right. So again, the short of it is, if you try to solve it by either substitution or elimination, and you get something that's true, right? 2 equals 2 was true, or if you just keep going and you get 0 equals 0, that's an infinite number of solutions, which means this is a dependent system. So if you get something true, if you're, let me back up one more step. If your variables disappear on you and you get a true statement like 2 equals 2, that's a dependent system, and there are an infinite number of solutions in that case. All right. Okay. What about this case? So be careful with this one. I'm going to rewrite the problem over here. We have 6x minus 7y equals 5. That's the top equation. Now, when I go to write the bottom equation, I could just copy it over here, but I should realize there's kind of a mismatch, right? I get 7y here minus 6x equals 3. Well, the problem there is that these aren't lining up with each other. This is x, this one's y. That's, not going to work out very well, right? It's going to make things more confusing. So what we want to do, especially if we're going to use the elimination method, otherwise called the addition method, is we want to make sure the x's and the y's are lined up. So I should put x first here. So when I go, sorry, I don't know why I undid that last part there. When I go to write my second equation, I'm going to start with the x term first. It's negative, so when I copy this over here, I'm going to put negative 6x first, and then positive 7y second. And that means I'll have to put a plus sign in front of that, equals 3. Right? And for the elimination method, for the addition method to work, when I add these two equations together, I need to be sure that one variable is going to get canceled out, and I see that will happen, right? The x's are ready to cancel out. And so I'll add these equations together. I don't have to do any other work to make this work out. And so the x's are going to cancel each other out, but the y's also do. So that wasn't my intention. You don't want both variables to necessarily cancel out, but when one cancels out, the other one cancels out as well. So the entire left-hand side just gets eliminated. And so whenever everything just disappears, that's what 0 is for, right? It's a placeholder for when you have nothing. On the right-hand side, we're going to get 8, right? 5 plus 3 is 8. And so our variables have disappeared, much like they did in the previous problem, right? We want to solve this for x. Well, the x just disappeared on us. This time we got something true, which meant we had an infinite number of solutions, which meant it was dependent. In this case, our variables disappeared on us, but we got something that was false, which means there are no solutions in this case. So that's how you tell the difference. If your variables disappear on you while you're trying to solve the system of equations, it is a special case. There are two special cases. It could either be no solution or it could be infinitely many solutions. So the funny thing is, complete opposite ends of the spectrum, right? So if your variables disappear, it's either no solutions at all or infinitely many solutions. The way you tell the difference between those two situations is whether this came out true or false. If it comes out false, that means there is no ordered pair that can satisfy both equations at the same time. If it comes out true, that means any ordered pair that works in one automatically works in the other. That means there's an infinite number of ways to satisfy both equations at the same time. So it really comes down to, did it come out true or did it come out false? Right. So it's false, so no solution, which means this is an inconsistent system. All right. And so I'd mark C. Now, they don't say no solution here, but empty set is the same thing as no solution. So they use a little bit of a different descriptor there, but it means the same thing. All right, so this video is already getting a little longer than it's supposed to be. I have, I think, 3 more examples. Yeah, 3 more. And so this one is back to normal. This is going to work out to be a normal system of equations. You'll get one solution from this. In this case, we're going to use the elimination method, also called the addition method. And I wanted to do this example because this is worst case scenario for the addition method, at least in terms of getting it set up. Now, I can't remember if this answer works out to be a fraction, but I guess worst case scenario would be all the work we're about to do now plus having fractions in your answer. I don't know if it's quite that bad, but this is sort of worst case scenario for how bad the addition method could be. So if I go ahead and just copy the equations over here, so you can see them a little bit better, and so I have some room to work. Here are my two equations. If I do what I've done the previous two times I've used the elimination method, and I just jump right into adding the equations together, mathematically speaking, it's not wrong to do this. You haven't made any mathematical mistakes by doing this. I add the left-hand sides together. I get 4x plus 3x, which is 7x. I add the right-hand sides together. I get negative 5y plus 7y, which is plus 2y. And then I add the right-hand side of the equation together. I might have said that funny. So I add the x's together, add the y's together, add the right-hand side together. It's negative 46 plus 39. That's going to be negative 7. I get this equation, which isn't wrong. It's also valid, right? So if 4x minus 5y equals 39, which it does in our system, and 3x plus 7y equals negative 46, which it does in our system, then it's also true that 7x plus 2y will equal negative 7. This is a true equation if these two are true. But it doesn't get me any closer to getting the solution to the system, right? What can I do with this? I'm in the same boat I was to begin with. I have x, I have y. There's no way for me to solve for one of the variables to get an answer going, right? So it's a dead end, right? You get something that's true, but it doesn't help you, right? In order for this method to be effective, I have to be sure that when I add the equations together, that's why it's called the elimination method. Nothing here got eliminated, so it didn't work. So this time I have to actually put in some work here to make sure a variable gets canceled out. So we have to first decide which variable do I want to see canceled. You can do x or you can do y. It's your choice. But I'm seeing y, I'm leaning more towards y because they're already opposite signs from each other. That helps. For a variable to cancel out, you have to have the same number but opposite sign. Then they cancel each other out. These already have the opposite sign. So all I have to do is make sure these come out with the same number. So if I could, I would turn the 5 into a 7, but there's no way to really do that by multiplication, because that's what we're going to have to do here, is multiply something to the 5. If I could multiply something to the 5 to turn it into a 7, that worked out nice. I mean, there is a number that works, but it's a fraction. Then I would do that. But instead, what I'm going to have to do is change both of these numbers. It's just like doing a common denominator. You have 5 and you have 7. What's a common number that these can both be multiplied up to? What would the common denominator be for 5 and 7? It would be 35. So that's our goal. I want to turn both of these numbers into a 35. That way they'll cancel each other out. I can make the top, I'm trying to think, what color could I use here that I haven't used? I guess blue I haven't used yet, right? I can turn this into a 35 by multiplying both sides of the equation by 7. Now this is kind of my lazy way of doing that. I'm putting parentheses around the whole equation, indicating that 7 is getting multiplied to both sides. 7 times 5 will make that a 35 here. I can make the bottom equation have a 35 in front of the y if I multiply it by 5. Right? 5 times 7 is going to give me 35 there. But I can't just multiply the 7 and the 5 to just the y terms, because that wouldn't keep the equation balanced out. So I have to multiply it to the entire left-hand side and the entire right-hand side. So all of these numbers have to get multiplied by 7. All of these numbers here have to get multiplied by 5. I'm distributing, if you will. All right, let's go and distribute it there. And so I'm going to end up with 28x minus 35y equals, I think I'm going to use my calculator here. It's getting kind of late in the video, and I just don't trust myself enough to do this calculation in my head. So we'll have 7 times 39, which is 273. All right, so I'm going to get 273 here. Multiply the bottom equation by 5. We're going to get 15x plus 35y equals 5 times negative 46. It'll be negative. Now this one I can do a little bit more easily. I think of first 5 times 40, which is 200, right? Because 5 times 4 is 20. So 5 times 40 would be 200. And then 5 times 6 will be 30. So it's going to be 230 when you put those two together. All right. Now I will add these equations together. So now let's give this another try. We'll add the left-hand sides together, add the right-hand sides together like we tried before. Here, the x's will combine together, and we will get, I believe it's 43x. Now the y's are going to cancel each other out. They're the same number, opposite sign, they cancel each other out. The right-hand sides, I add those together, and I luckily get 43. 43 is not the friendliest number. And like I said, you shouldn't be getting crazy fractions as your answer. So you really got to hope you get something over here that's going to work out nice. And so that works out really nice, right? So we end up with 43x equals 43. I solve that for x by dividing 43 on both sides, and I get a really nice answer here, which is 1. But I'm just warning you, sometimes on some of your homework problems, you're going to get answers that are fractions. I haven't encountered that in my video. I chose my problems wisely, I guess. But just be aware that when you're doing the homework, you should be on the lookout. You could get fractions. It doesn't mean you did the problem wrong. All right. So we get x equals 1, but just like we had to do before, we still need to find y. So I'm going to take this value for x, plug it back into one of the original equations. This one, it's a crapshoot either way, right? I mean, neither of these equations look very friendly to work with. I'll just pick the bottom one. It doesn't matter. I should get the same answer for y either way. I try to pick the equation that's going to be less work, but these are going to be equal amounts of work. It doesn't matter which equation I pick. All right, so I'm going to get 3x plus 7y equals negative 46. I'm going to plug in 1 for x, and then I'm going to solve for y. So I'll get 3 plus 7y equals negative 46. I will subtract the 3, so it's going to be some work here. Subtract the 3 to the other side. I get 7y equals negative 49. And then, I don't want to use that color. And then we divide by 7 on both sides, which gives me y equals negative 7. So again, works out nice. And so we end up getting 1 comma negative 7 as our final answer there. So again, that's close to worst case scenario for what you might expect on these system of equations. All right, let's take a look at a couple of word problems to get this video over with. So a collection of dimes and quarters is worth $5.30. There are 38 coins in all. Find how many of each there are. So this is pretty common type of word problem for system of equations. It's a coin problem. We have 2 different types of coins, and we're given the value of those coins and the number of those coins. So a rule of thumb for solving a word problem like this is for however many unknowns you have, that's how many equations you have to have. So the number of variables is also the number of equations that you have to develop. In this case, we have 2 unknowns, the dimes and the quarters. We don't know those, right? That's 2 things we're looking for. So we have to have 2 equations in order to get a solution. That's why they're giving us 2 pieces of information. The value of the coins will be one equation. The number of the coins will be the other equation. And using those 2 equations, we can solve for these 2 variables. Right, so I feel like I'm saying it. I feel like there's a better way to say it that I usually say it as, but it's not coming to me. So the number of unknowns is also the number of equations you need to have. Now, what I want to warn you against is being vague about your description of these unknowns. So an unknown is going to be a variable, right? So any values that we don't know, we have to use variables to represent those values. I don't know the dimes, right? And so you might say, you can use X and Y, but I'm going to use D for dimes, Q for quarters. Now, I'm doing this on purpose. If you're being intentionally vague about that, and you're saying, well, let's have D be the dimes and Q be the quarters, you might set up your equations incorrectly. Because you're going to say, well, if I take the dimes and the quarters, that adds up to $5.30. So I'll have students that do this as their equation. And then they'll say, and also, if you take the dimes and the quarters, there's 38 of them in all, right? So dimes and quarters is going to be 38 coins. And this is going to be an improper way of setting up the equations because you're using these variables in 2 different ways. Because you're being vague up here, you're allowing yourself to think of these in really 2 different ways, even though you're not saying it that way, right? So here, for the bottom equation, D is representing the number of dimes plus the number of quarters is 38 coins altogether, right? But in the top equation, you're using D as the value of the dimes, plus the value of the quarters is $5.30, right? So think about it like this. Like if I say, D is equal to 8, does that mean you have 8 dimes, or does it mean you have $8, right? In dimes, right? So what is that going to represent? You have to choose, right? You can't just say, dimes is 8. What about the dimes is 8? Is it $8 worth of dimes, or is it 8 dimes, which is just worth 80 cents, right? You see the difference there. And so the easiest way to proceed in this problem is to let the variable represent the number of those coins. So D is going to be the number of dimes, and Q is going to be the number of quarters. And so you see, if you're specific about it, the bottom equation still makes perfect sense. The number of dimes plus the number of quarters is 38 coins altogether. So this equation is still good. The top equation, however, doesn't make sense anymore. The number of dimes plus the number of quarters shouldn't add up to the value of those coins. So to get the value, let's say you have 8 dimes. What's the value of those dimes? It's 80 cents. The way you get that is you multiply it by 0.10, and that gives you the value, right, of the dimes. So if you have 8 dimes altogether, that's 80 cents in value. So we'll do the same thing over here, right? Except we'll do it with the variable, right? So if I have the number of dimes, I want to multiply that by 0.10 to get the value of the dimes. And if I have Q as the number of quarters, I multiply that by 0.25 to get the value of the quarters, right? If I have 3 quarters, that's the number I have. I multiply that by 0.25 to get the value of those quarters, which is 75 cents, 0.75, right? So this is what your 2 equations should look like. All right, then we're going to solve this. Now that we have our 2 equations, it's a system of equations with 2 variables, just like the problems we were doing earlier in the video. So to solve this system of equations, I will either use the substitution method or the elimination method. You rarely ever want to use the graphing technique. So either substitution or elimination method. And while my variables are lined up nicely, you might consider doing the elimination method. I think that's what Math Excel would have you do. I think this bottom equation is so easy to solve that I prefer to do substitution method on these problems. So again, to do the substitution method, you have to solve one of your equations for one of your variables. And so I'm going to solve the bottom equation for D, right? So I'll subtract Q to the other side, and I get D is equal to 38 minus Q. I'll plug that into my top equation, the equation I haven't used yet, right? And so I'm sorry, I'm making a mess of my process here, but so I'm going to take this top equation, which is 0.10 D plus 0.25 Q equals 530. And in place of D, I'm going to plug in 38 minus Q. The rest of it stays the same. So I'll still have the 0.10 in front of that. So that means I want to put parentheses around that. Plus 0.25 Q equals 5.30 Q. Right. And then now I can solve this equation for Q to find out the number of quarters. So I'm going to distribute the 0.10. So it's going to be 3.8 minus 0.10 Q plus 0.25 Q equals $5.30. Then we will combine. I did this earlier. I'm going to do the same thing here. Do 2 things at once. Combine the Q's together, but while I'm at it, I'll subtract the 3.8 to the other side, which, since we're dealing with money, you might want to throw a 0 on that. It's like $3.80, right? So subtract the 3.80 to the other side. Now, my recollection is there is a way for me to scroll down. Let's see. Okay, good. All right. Because I'm going to need a little more space here. So I'm going to end up with, combining these together, I'll get 0.15 Q. And when I subtract this over here, I'm going to get, how much is that going to be? $1.50? It's going to be $1.50. Right. And then we will subtract the 0.15 to the other side. Now, earlier I was warning you that when you're solving a system of equations, the answers don't have to work out nice. In general, that's true, but for word problems, that may not be the case. So here, this has to work out as a nice number. You cannot have half a quarter. You can't have 3.5 quarters, right? It either has to be 3 quarters or 4 quarters. So if you're getting a decimal or a fraction as an answer here, that is a serious issue. That means you made a mistake in how you set up the equations or in how you solve them, and you need to go back and review the work that you did. So here, this works out nice. I get Q is equal to 10. That means there's 10 quarters. So how many dimes are there going to be? We will take Q equals 10, plug it back into one of our original equations. I think this would be a great place to plug it in. And we'll get that the number of dimes is 38 minus the number of quarters, which is 10. And so I'm going to get that the number of dimes, it's starting to glitch on me, the number of dimes is equal to 28. So 28 dimes and 10 quarters would fit that description. This will be $5.30 altogether, and it's 38 coins altogether. And so you could check that if you wanted to make sure that it works out the right way. 10 quarters is $2.50 plus $2.80. That's $5.30. And it's also the right number of coins. It's 38 coins. All right. Okay, we hit the 1 hour mark. Sorry about that. Last example. Right. The city zoo has different admission prices for adults and children. When 3 adults and 2 children went to the zoo, the bill was $79.80. If 2 adults and 3 children got in for $75.60, then what is the price of an adult's ticket and what is the price of a child's ticket? So again, there's 2 unknown values in this problem, which means we have to find 2 equations in order to get a solution. The unknown values are the price of an adult ticket. So again, be specific here. Don't say, oh, it's adult ticket, child ticket. It's the price of an adult ticket, which I'll call A. You could call it X if you want, but I'm going to just use A for adult, and the price of a child ticket, which I will call C. Right. Now this problem, students usually do pretty well with setting up the equations because the equations are quite literal here. 3 adults and 2 children, right? So that's 3 adults, 3 times A, plus 2 children, that's 2 times C. And if you take that total, it has to add up to $79.80, right? So we're taking 3 times the price of an adult ticket to find out how much it costs for the adults to get in, and then 2 times the price of a child's ticket to find out how much it costs for the children to get in. And when you add that together, the total due is $79.80 according to the problem. If 2 adults and 3 children got in for $75.60, then we want to use that information to find out how much the adult ticket was, how much the child ticket was. All right, so there's my 2 equations, right? 2 unknown values. I have 2 equations now, so I can solve and find out the value of those 2 variables. This one, substitution method, is not looking ideal to me. I could use it. It's still valid, but it's asking for trouble. I mean, you're really going to be putting yourself through a lot of anguish if you're doing this by substitution method, right? Because you'd have to solve one of these equations for one of these variables. Am I going to solve this one for A? That doesn't look very pleasant. Am I going to solve this one for C? Also doesn't look pleasant, right? There's no easy variable to solve for here. So we are going to be better off using the elimination method. The variables are already lined up for us, but if I just add them together the way they are, nothing gets eliminated. So I have to do some work here to make sure a variable is eliminated when I add these equations together. I have to decide first, which variable do I want to eliminate? Let's go with, it doesn't matter, it's the same amount of work either way. I'm going to choose A. So let's have A be eliminated first. If I want A to get eliminated, I have to get the same number here, but opposite sign. So I have a 3 and I have a 2. What's a common number that both of these could be multiplied up to? It's like doing a common denominator. The answer is 6, right? I can make both of these equal 6. I can multiply the top equation by 2, right? Because 2 times 3 will give me 6 here. And then multiply the bottom equation by 3. But if that's all I do, I'll get 6a in the first equation, and I'll get 6a in the second equation, which is good, but they still wouldn't cancel each other out because they're both positive. 6a and 6a would be 12a. So I need to make sure one of these is negative. So while I'm at it, I can make sure one of them comes out negative by multiplying by a negative sign. You don't want to do that to both of them because then they'd both be negative and you'd be back in the same boat, right? You want one to be negative, but keep the other one positive. So I will multiply the top equation by -2. That'll make this a negative 6a, make that a positive 6a. They'll cancel each other out. So the top equation becomes negative 6a minus 4c equals, let's see, I'm sorry, I better just do the calculation here. So I'll have 2 times 7980. I should be able to do that in my head, but I just feel like I'm out of energy here, mental energy. So that was, I think I already forgot what I put there. It'll be negative, because it's negative times a positive. 159.60 is what I remember it saying. Yeah, 159.60. Okay. And I'm going to throw the 0 on the end of that because we're talking about money again. So I like to go to 2 decimal places with that. The bottom equation will be positive 6a plus 9c equals, we'll have 3 times 7560. It's going to be 226.80. So let's see if I can remember that. 226. It's funny how like random numbers might be harder to remember, but when it's money, for some reason it just seems easier to remember. Okay, so we're going to, now that these will cancel out, I'm going to go ahead and add these together, just like we did before. The a's are going to cancel each other out. We'll have negative 4c plus 9c, which is going to be 5c, equals, we'll have 226.80 minus 159.60. Minus 159.6, and we're going to get 67.2. So $67.20. All right, now we'll divide that by 5 to solve it for C, and this will tell me the cost of a child's ticket. So divide by 5, and we get $13.44. So that's a reasonable dollar amount. Now, if we got more than 2 decimal places, you might be a little suspicious of that. So if your answer was like 9.3758, that's not really what you would expect for a well-formed problem when you're talking about money. Should be correct down to the nearest penny. And if it's going to be an answer like that with money, usually the directions will tell you, and it'll say something like round to the 2nd decimal place, letting you know that you might get an answer that's not the nicest answer. But this is a good answer, $13.44. That's how much a child's ticket costs. How do I find the cost of the adult's ticket? I have to take this value for C, plug it back into one of the original equations before you multiplied it by 2 and 3, right? Because these numbers are kind of big. Let's go back to the original numbers. And again, it's going to be the same amount of work either way. I guess I'll just plug it into the bottom equation. So I'm going to plug it in here. So I'll do that over here. We'll have 2a, let's make sure I have enough room, 2a plus 3 times, instead of C, I'm going to plug in $13.44 equals $75.60. All right. And so I'll multiply these together. Again, I should be able to do this without a calculator, but I'm feeling like I just don't have the energy to do that. $40.32. 32 cents equals 75.60. And then now I'm writing numbers out of order. This is still going to be 2a, and I'm sorry if that's kind of hard to read, but that's an a right there. All right, then we solve it for a, kind of the same boring old routine. Subtract the 40.32 to the other side, so I'll have 75.60 minus, now this is going to say negative because I'm subtracting it backwards, because I already had the 40.32 in my calculator, so I decided to subtract 75.6 from that. So it's going to give me the right number, but it'll be the wrong sign. So it's going to be 35.28, right? I'm just going to drop the negative sign since I subtracted it backwards. 35.28 is equal to 2a. We divide by 2 on both sides, and we get a is equal to, divide by 2, 17.64. So $17.64 for an adult's ticket. All right, so make sure when you get your results here, especially if you use X and Y instead of A and C, so I used A and C so I'd know which one was which. C for child, A for adult. But if you use X and Y, you might forget which one was adult, which one was child. And it matters when you type it into Math Excel. It wants to know how much is the adult ticket, how much is the child ticket. I guess another way you would know is the bigger one's obviously the adult ticket, the smaller one's the child's ticket. But C for child's ticket, so C would get plugged in here, 13.44 for the child's ticket. A for adult ticket, that's $17.64. And so that would be the answer in that case. So that concludes the lesson on section 5.1. Thank you for watching.